Imagine you're an astronaut, making a critical repair miles above the Earth. Or maybe you're a surgical robot performing some delicate maneuver deep inside a patient.
In those kinds of high-stakes situations, you absolutely need to know exactly how much force you're applying.
Exactly. Not a guess, not an estimate, but a perfectly calibrated measurement.
And that perfect measurement, that's the kind of mechanical precision we just take for granted until, it fails. I mean, think about the tension on a braking cable for a fighter jet.
Or even the knot needed to secure a lifeline. The challenge, I guess, is that our modern solutions for this always rely on electronic sensors.
Right, and those sensors can be bulky, they can fail, especially in weird conditions like inside the human body,
Yeah.
and they're incredibly expensive to put everywhere.
So there's this huge technological gap. We need precise force feedback in places where our high-tech electronics just can't go. And that is the core conflicts we're diving into today.
Yep.
Our mission is to understand a really groundbreaking strategy that uses, of all things, the humble slipknot to encode and deliver mechanical force. They're basically turning a piece of string into a smart sensor.
It's incredible. We're dissecting the paper Slipknot Gauged Mechanical Transmission and Robotic Operation, which was published in the journal Nature.
A huge deal.
Oh, absolutely. This work was led by a whole team, including Yating Xu, Jiexin Cao, Tao Feng, and Kai Hengzheng, mostly from Zhejiang University and Sir Renshaw Hospital. They've essentially found a way to hardwire intelligence right into a fiber.
Okay, so let's start where the stakes are probably the highest
Yeah.
inside the human body. When a surgeon is closing an incision or connecting two organs,
Yeah.
well, what's that called? Anastomosis.
Anastomosis, yeah.
Yeah.
It is one of the most mechanically delicate things you can possibly do.
And it's astonishingly low tech, right, for such a critical moment.
It really is.
Yeah.
Right now, when a surgeon ties a knot, they're often just relying on visual estimation. They look at how much the tissue deforms or stretches.
So it's subjective. It depends on how tired the surgeon is, or if it's been a long day.
Completely subjective. And when you're talking about soft, vital tissues, that subjectivity can have, well, catastrophic results.
I can imagine what happens.
The consequences of getting the tension wrong are pretty much binary, life or death. If the knot is tied with too much force, you just crush the tissue. The medical term is ischemia. You're literally cutting off the blood supply, the tissue dies, and the whole repair fails.
Wow. So you've choked off the life source of the very thing you were trying to fix. What about the other way? Too loose.
If the force is too little, the repair just doesn't hold. It can lead to something called dehiscence, or in the gut, anastomotic
That
leaks.
sounds bad.
It's incredibly dangerous. The wound separates, it leaks, and the researchers cite that this can increase patient mortality by over 30% in some cases.
30%. Okay. So surgeons need an objective, repeatable way to do this.
Yeah.
Which brings us to this new idea, knots as code.
Exactly. That's the conceptual leap here.
It sounds like something out of a spy movie, programming data into a thread. How does this slipknot gauge strategy actually work?
It's basically a two-step mechanical dance. The first step is what they call writing the force. So when the researchers tie the slipknot in the first place, they do it with a very, very specific amount of tension.
Wow.
And that input force, they call it Nadal tying, it dictates all the internal friction and the elastic deformation of the knot. The knot becomes, mechanically preloaded with that information.
So that's how they program it, with that initial force, the firing print.
Precisely. Then you have step 2, which is reading the force. So when the end user, a surgeon or a robot, pulls on the string, the slipknot resists.
Right.
It resists until the tension hits a specific critical point. And at that moment, the knot just pops open, releasing all that encoded force as a sharp, unmistakable peak force signal. They call that peaker.
Okay, so this is the crucial part, because I want to be crystal clear. Is that peak force the same as the force they use to program it?
That's a great question, and it's the common assumption, but no. The values aren't necessarily equal. They are, however, consistently related.
Ah, okay.
That input force, Fnai, it sets the geometry and the friction inside the knot, which in turn determines a very reliable opening force, Pfaffen. For instance, they showed that if they tied a knot with, say, 7.5 newtons of force,
Okay.
the force required to then open it, the 5 peak was consistently around 2.945 newtons.
Well, the magic isn't that the forces are equal. It's the absolute consistency of that output force.
Exactly. The knot holds the information and releases it like a perfect mechanical stop sign. And here's your wow fact on that consistency.
Yeah, Dami.
In 500 independent tests, the variation in that measured Pfaffy was tiny. They achieved a consistency of 95.4%.
95.4%. That's the kind of reliability you need for medicine. It's just from the geometry of a knot.
Purely from the physics of the knot. The mechanical analysis backs it all up. They even confirmed the opening is linked to a fundamental topological change, something known in mathematics as a Reidemeister move.
So it's fundamentally stable.
Deeply stable. It's reliable across different speeds, and even after being stored for over a month.
So they have this perfectly consistent mechanical sensor. How do they get it from the lab bench into an actual operating room?
They packaged it into something they called the sliputure.
Sliputure.
I like it. It's simple, really. It's just a common surgical suture that's connected in series with one of these preset slip knots.
And the instruction for the surgeon becomes foolproof. Just pull the suture until you feel the slip knot open.
Exactly. That distinct, sudden opening acts as a physical, tactile indicator.
So since that opening force, Sleepy's pre-calibrated, the final tying force applied to the patient's tissue is automatically guaranteed to be the right amount. It just takes all the guesswork out of it.
It makes sure the tension lands right in that sweet spot every single time. For their tests on rats, they figured out the optimal force was between about 0.3 and 2.3 newtons, and the sliputure just ensures the surgeon hits that target.
This has to be a huge deal for training, right? I mean, senior surgeons with decades of practice are obviously going to be more precise than junior surgeons.
It's a true equalizer. This is one of the most staggering results. When junior surgeons use the sliputure, their knotting force precision improved by an incredible 121%.
121%. That's not just a small improvement. That's like giving a less experienced surgeon the muscle memory of a veteran.
That is the perfect way to put it. The most impactful finding was that junior surgeons using the sliputure achieved performance that was equivalent to senior surgeons using traditional methods. It's like a low-cost mechanical mentor.
That's an incredible claim. So were there any drawbacks? Like, is the material bulkier, or does the knot opening cause any extra tissue damage?
That's a great question. And they looked at that. They used pressure-sensitive films and found the opposite was true. The pressure from the sliputures was actually much tighter and more consistently applied. Less variability.
Which would mean less trauma.
Yeah.
So what about the real-world impact? Did this actually translate to better healing in the rat model?
It did, and the clinical outcomes were really promising. They measured something called burst pressure, which is a key indicator of healing strength.
Okay.
The tissues repaired with sliputures reached healthy levels by the 5th day after the operation.
And the control group?
That was 2 full days earlier than the group with common sutures.
2 days faster healing. In hospital terms, that's a massive deal. It could reduce stay times, risk of infection.
Everything. And there's more. They used a technique called LSCI to measure blood flow. It confirmed way better restoration of blood supply in the sliputure group, and, crucially, they saw significantly fewer post-surgical adhesions.
What's an adhesion?
It's basically internal scar tissue that can cause complications. In the common suture group, all 10 rats had adhesions.
10 out of 10. And the sliputure group?
Only 3 out of 10.
Wow. So less inflammation, faster recovery, fewer complications. It really underscores how critical that precise tension is.
It's everything. Now let's pivot to the machines.
Right, robotics. Because even a system like the Da Vinci surgical robot, which is famous for its precision, still lacks direct force feedback.
It's a huge blind spot. The surgeons using them still rely on visual cues, just like they do with manual surgery. The robot can move with micron accuracy, but it can't feel the tissue.
But the sliputure principle fixes this too, right? Because the knot opening is a visible event.
Exactly. The robot can simply be trained to watch for the physical sign.
So is it just a simple camera? Or do they need something more complex?
That's where they integrated some AI. They customized a Da Vinci system with a vision-based detection system they cleverly named SlipknotNet.
SlipknotNet, love it.
It's a type of neural network, an AI, that's been trained specifically to recognize the exact moment that Slipknot opens on the video feed.
So the AI is the translator. It sees the mechanical signal, the knot opening, and turns it into a digital command for the robot.
You got it. The moment SlipknotNet detects that opening, it automatically issues a stop command to the robotic arm. It just completely prevents the robot from overpulling.
And how much did this simple mechanical input improve the billion-dollar robot?
The robotic system improved its suturing precision by 71.3% in their models, and you could see it. The tissues repaired with the sliputure were flat and even. The ones with common sutures often looked kind of extruded or bulging from inconsistent force.
So the slip knot gives the robot the one thing it was missing. a sense of touch, mechanical intelligence.
And it goes beyond surgery. They also tested this as a kind of safety fuse, like a low-cost mechanical circuit breaker in a robotic arm.
A fuse made of string. That's fantastic. How does that protect the machine or, the humans around it?
So they just place a slip knot in the arm's actuation pathway in its tendons. If the arm gets overloaded, say it bumps into a person or hits something unexpected, the tension spikes past that preset fee path.
And the knot just pops open.
The knot opens, tension is released instantly. The force transmission is just cut physically and harmlessly.
Which protects the human from getting hurt and probably saves the owner a ton of money by preventing damage to the robot's gears and motors, all without a single complex electronic sensor.
And we really have to stress the economic side of this. Those electronic force sensors are prohibitively expensive. The researchers noted that sliputures can be mass fabricated easily and automatically, making this a super economical solution, especially for, resource-limited hospitals around the world.
This deep dive into the work by Zhu and his colleagues has really shown that the most sophisticated solutions can be rooted in the simplest principles. Let's quickly summarize the key takeaways.
Okay. First, remember that the slipknot is a highly reliable mechanical sensor. It accurately encodes a force and releases it with over 95% consistency. It's a non-electronic force gauge that's perfect for extreme environments.
Second, the sliputure is a clinical necessity. It improved knot tying precision for junior surgeons by 121%, basically matching the performance of veterans, which then leads to faster healing and fewer complications.
And finally, this simple mechanism provides a high-tech, low-cost safety solution. It boosted robotic surgery precision by over 71%, and it acts as an instant, purely mechanical safety fuse, protecting both people and machines.
This research really gets at what the authors call mechano-intelligence. It shows that something as fundamental as topology, the study of knots and shapes, can perform these sophisticated control functions we usually think require advanced electronics.
It completely shifts your perspective. Instead of always looking to silicon or software for intelligence, this shows that, nature and fundamental mechanics offer these incredibly reliable, resilient control systems. We even see similar things happening at the molecular level with knotted DNA.
Which leaves us with a final provocative thought for you to chew on. If we can solve cutting-edge problems in robotics and medicine with a simple knot, a technology that's literally thousands of years old, what other seemingly trivial, overlooked physical structures in our world are just waiting to be engineered into the next major technological breakthrough?